drift with me into the most relaxing facts about our solar system. A gentle journey from the sun's soft breath at the heliopause to quiet oceans beneath distant ice. We will trace slow seasons on tilted worlds, lantern-bright rings and tides that move like a global heartbeat. Calm wonders designed to soothe, not startle. If this peaceful tour helps you unwind, please like the video, subscribe for more night-friendly science, and tap the bell to rest with every new episode. At the far edge of the solar system, the sun exhales a steady wind of charged particles that drifts outward in all directions, thinning with distance, until it begins to slow and fold against the breath of the galaxy beyond. And this gentle meeting place is called the heliopause, a boundary not of walls, but of balances where motion becomes soft enough to notice where the rhythm of the sun's long pulse becomes a hush. The wind begins closer in with warmth and speed, then crosses a quiet threshold named the termination shock, where it cools and slackens, and the space between that threshold and the heliopause forms a vast cushion known as the heliosheath, a region where the sun's influence lingers like the last light after evening. Two small messengers, Voyager 1 and Voyager 2, launched by the National Aeronautics and Space Administration in the late 1970s, have moved patiently through this outer calm, sending faint signals that carry a portrait of the boundary as it breathes. In the year 2004, one of them felt the slowdown that marks the termination shock, and in the year 2007, the other felt it too, each crossing a slightly different distance, because the solar system sits not in a perfect bubble, but in a flowing shape that ripples with the seasons of the sun. In the late summer of the year 2012, far beyond the orbit of Pluto Voyager, one moved through the heliopause into the local interstellar medium, and in the autumn of the year 2018, Voyager 2 followed each spacecraft, confirming that the sun's breath ends, not with a sharp edge, but with a gradual easing like surf that tires over a long stretch of sand. The distances involved are peaceful in their enormity, hundreds of billions of kilometers, which astronomers describe as well over 100 astronomical units. Each astronomical unit being the average span between Earth and the Sun, and inside that scale the solar system feels like a lantern whose glow fades to starlight at its edge. The particles that make up the solar wind whisper outward at many hundreds of kilometers per second closer to the Sun, then lose energy as they push against the sparse gas between the stars, and the tug of the galaxy presses back with an almost imperceptible firmness, shaping the heliosphere into something a little like a droplet drawn out by motion through a river. Magnetic fields thread this place, lines of force from the sun mingling with lines from interstellar space, and together they weave a gentle net that turns incoming cosmic rays aside, so that the inner worlds live in a shielded calm that varies with the sun's cycle of activity. That cycle itself moves with an unhurried rhythm of roughly 11 years from one peak to another, a slow waxing and waning of sunspots and flares, and the size of the heliosphere grows and shrinks accordingly, not abruptly, but with the tempo of a deep breath, so that the boundary that checked a spacecraft 1 decade would sit a little nearer or a little farther in the next. Instruments on board the Voyagers count cosmic rays like raindrops, and call out the change when the shelter thins, and they listen to the low radio note of interstellar plasma ringing after a solar outburst sweeps past, and those sounds translated to numbers tell of a boundary that holds its shape but not its exact place. The European Space Agency and the National Aeronautics and Space Administration follow this rhythm with other craft closer to the Sun, and together these missions sketch a picture of the whole, a lantern of wind whose flame steadies the weather of space. The temperature out there is cold enough to still movement in most things, yet the plasma that fills the heliosheath keeps a mild warmth of motion, the kind of heat that belongs more to spread than to spark, and the pressure that balances the sun's wind is not much more than a tender touch. Dust grains that left comets long ago drift outward and may graze this boundary before turning each grain a quiet witness to the traffic of the ages and the rare neutral atoms that wander inward from the galaxy carry a trace of its chemistry, allowing sensors to taste the interstellar environment without ever leaving the sun's care. Even the shape of the heliosphere, long pictured as a comet, like tail blown back by a headwind, is now thought to be rounder and more blunted, perhaps shaped like a softly pressed crocus bud. A reminder that the simplest picture is sometimes only a beginning and that the truth may be gentler. The calm mystery here lies in how such a large, faint boundary can be so steady, while constantly changing a paradox that sleep can hold without solving. And the anomaly that invites thought is that the two Voyager crossings did not happen at the same kind of place, one entering a denser interstellar plasma than expected, the other measuring a different balance of magnetic field direction, as if the edge had local weather of its own. There is a serene speculation that the heliosphere sometimes gathers ripples where interstellar magnetic folds brush against it, and those ripples would thicken or thin the shield in patches, the way high clouds shade a field, changing the count of cosmic rays that reach inward, and perhaps these gentle variations play a role in the slow drift of radiation in the inner system, on scales longer than human lifetimes. The boundary also speaks of origins, because the Sun was born in a cluster where winds from sibling stars and ancient supernova blast waves swept the gas clean, and the size of the heliosphere today whispers how the Sun, now travelling alone, still carries a memory of pressure and speed balanced against the wider galaxy. In the distant future, the Sun will move through different interstellar neighbourhoods into pockets of denser or thinner gas, and the heliosphere will swell or compress with those changes, a lantern trimmed or opened by the invisible breeze. Yet always it will remain a place of soft gradations rather than hard partitions, a sign that in space, as in a quiet tide pool, edges are often places where different waters mingle rather than collide. The most relaxing fact of all may be that this edge holds that its motion is measured and patient, that the protector of planets is broad and light and resilient, a structure made not of stone or ice but of steadiness itself, and that our instruments, small and long-lived, continue to hum their reports across a gulf so large that light itself needs many hours to carry each message home. That light travels through the darkness with the simple certainty of a beam crossing a room, and each time it arrives, the picture of the heliosphere becomes a little more complete, not with sudden revelations but with gentle strokes, and the question that rises is not urgent at all, only restful, only curious about how far the calm extends, how the breath of a star becomes part of the breath of a galaxy, and whether the boundary, now beyond 100 astronomical units, quietly swells on some years or settles inward on others in a cycle that will keep repeating as long as the sun shines. In that thought, the solar system feels both large and sheltered, a home with a softly lit porch, open to the night, and yet warmed by a centre, the kind of image that helps the mind ease into sleep, while the universe continues its measured turning, always there, always calm at the edge where winds meet and rest. Beyond the orbit of Neptune, where sunlight arrives more than 1,000 times fainter than it does at Earth, a broad ring of ancient worlds drifts in a hush that feels like the preserved quiet of the early solar system. This is the Kuiper Belt, a realm of small planets, dwarf planets, and countless lesser bodies made of rock bound with simple ices, all moving in orbits that take centuries to complete, all keeping temperatures that hover about 40 degrees above absolute zero. The light here is thin but steady, and it paints surfaces in gentle shades of grey, tan and rust colours brought on by space weathering and by complex organic residues that astronomers call tholins, a word for mixtures made when sunlight and cosmic rays slowly alter methane and nitrogen frost over spans of time longer than any recorded history. Pluto glides through this region with its small companion Charon, and together they turn as a double world their shared gravity, keeping a careful balance that lets lighter ice creep across their faces in seasons that move slowly year by year. The National Aeronautics and Space Administration sent the New Horizons spacecraft on a quiet crossing that reached Pluto in the year 2015, and the pictures that came back revealed mountains of water ice as strong as rock in that cold plains of nitrogen ice that may ebb and flow with the seasons, and a haze that stacks in delicate layers as gentle sunlight drives faint chemistry in an atmosphere measured in whisper-thin units of pressure. After that encounter, the spacecraft continued into the belt and met a smaller body named Arakoth on the first day of the year 2019, and there it saw two lobes joined together like a snowman pressed by careful hands, each lobe flattened and softly rounded with a narrow neck. Between them, a form that suggests a meeting so gentle that it preserved the original shapes. The stillness implied by that contact rests like a clue. In this distant region, many bodies seem to have formed not with violent collisions but with slow gathering and tender mergers, as if the early solar system in this zone was a nursery where little worlds drifted and joined under a blanket of calm. The Kuiper belt shows families of orbits that keep time with Neptune in quiet resonances, where the gravity of the distant giant tugs at regular intervals that guide and protect paths rather than disrupt them. Pluto is the most famous member of a 2 to 3 orbital resonance, completing 2 turns around the Sun for every 3 turns of Neptune, a rhythm that prevents close approaches and allows Pluto to cross inside Neptune's orbit in projection without risk of a meeting. Farther out lies a group called the Cold Classical Belt, where many bodies move in nearly circular, gently tilted paths that probably preserve the original arrangement of the planet-building disk. And among these worlds, a surprising number are binaries, 2 partners circling a shared centre, as if the region still remembers the delicate threads that brought grains together. Surfaces here keep a record of slow changes. Methane freezes into frost that brightens a young crater, then darkens under sunlight that is weak but persistent. Nitrogen shifts from pole to pole over seasons that measure in human lifetimes. Water ice underlies everything like a bedrock made stable by deep cold. When a body happens to pass in front of a distant star, the star's light can blink or dim, and by timing that blink with great care, astronomers learn the size and shape of the foreground world and sometimes find a ring or a haze. A ring has been seen around the dwarf planet Haumea. Closer in the belt, a narrow loop of particles that circles a fast-spinning body, a reminder that even small worlds can gather companions made of shared debris. Eris farther out carries a moon and shines with a brightness that suggests a surface refreshed by volatile frost. Makemake shows a hint of the same. Quar and many others carry stories in their colours and densities that speak of mixed rock and ice in varying proportions. Even the distribution of colours across the belt from neutral grey to deep red hints at where sunlight and interstellar radiation altered primordial ices differently, perhaps reflecting the places where these bodies formed before the giant planets drifted to their current homes. The belt is not empty between its larger members, but filled with cobbles, boulders, and dust too faint to see directly, all moving slowly enough that many encounters are more like sidelong glances than strikes. Over spans of time measured in hundreds of millions of years, gentle collisions and distant tugs can change a path just enough to send a voyager inward where it becomes a centaur that crosses the giant planets, and later a short-period comet that brings its stored ices into the inner sunlight in measured bursts. When such a visitor sheds gas and dust near the sun, it draws out a tail that points away from the star, and the grains it leaves behind spread into streams that Earth may someday cross, becoming a meteor shower that unspools across a night in a slow and comforting rhythm. In this way, the Kuiper belt contributes quiet gifts to the inner system, not all at once but in patient intervals. The mysteries here are not flamboyant, they are gentle. Why do so many small worlds form binary pairs, and what soft conditions allowed them to remain bound for billions of years without being torn apart by passing giants or distant encounters? Why do some keep bright patches that suggest recent frost, while others are uniformly dark as if time had equalized everything? Why does the cold classical belt hold its calm, while other regions show scars of migration and stirring? One answer lies in the idea that Neptune itself moved outward early on, shepherding some bodies into resonances while leaving others undisturbed, and if that migration happened slowly and smoothly, it could have preserved the quiet order of the cold belt while populating the resonant families with travellers. The timescales for these changes reach back to the first tens of millions of years after the Sun formed a period that left no direct witness except the survivors at the edge. The Kuiper belt thus acts as an archive where chemistry and orbit together store memory. That memory is in reach because spacecraft can travel there, but it remains soft and open to interpretation because each visit is brief and each image captures only a moment in long seasons. Even from Earth, large telescopes on quiet mountaintops have learned to listen for the faintest light these worlds reflect, measuring subtle colours that hint at methane, nitrogen, and water in different proportions, and watching for occultations that like a heartbeat reveal size and shape with each flutter. The calm continues in the slow drift of light itself. It takes many hours for a radio signal to travel from a spacecraft at the belt back to the deep dish antennas that wait on Earth, and in those hours the scene hardly changes so that when the signal arrives it feels like a postcard from a place that holds still. There is comfort in that steadiness. The Kuiper belt stands as a gentle borderland, not a sharp edge, but a wide meadow beyond which the sun's grip eases and the stars claim more of the sky. Within it worlds keep to their lanes, thin atmospheres come and go with the softness of frost, and the materials that built planets remain in their original packaging, mostly unopened, still cool. The quiet question that rises is as simple as it is enduring: how many stories of the early solar system still sleep here, and how many will wake as future missions pass through, not to disturb but to witness, and to show that in the far blue twilight beyond Neptune, the universe remembers how to move slowly. Comets move through the solar system like patient archivists, carrying in their small bodies the gentle record of the cloud from which the sun and planets formed, and their paths stretched into long ellipses return in their own unhurried time, some after a human lifetime, some after spans that reach beyond written history. Far from the sun, in a sphere named the Oort cloud that likely begins at distances of tens of thousands of astronomical units, trillions of icy objects drift in a deep freeze where sunlight is a faraway glow, and when a passing star or the slow tug of the galaxy gives one a slight nudge, the object begins a journey inward, falling toward the light with dignity, conserving the ancient order of its path. Closer in the Kuiper belt beyond Neptune, another population of icy bodies can become scattered and reshaped by gravity into shorter period comets that return in spans of decades or centuries, making a quiet rhythm that human generations can observe again and again. As a comet approaches the inner system and the sun warms its surface, the simple ices that make up its crust begin to sublimate, turning straight from solid to gas, and this gentle outgassing lifts dust and grains into a surrounding cloud called the coma, a luminous envelope that grows until it may stretch wider than a planet, even though the nucleus at its heart remains only a few kilometers across. The gas in the coma, stirred by the solar wind, becomes ionized and points a faint tail away from the sun, while the lifted dust, heavier and slower, streams into a second tail that curves along the comet's path like a soft brush stroke. Each tail is a sign of direction as well as chemistry, a picture drawn by physics that uses light and charged particles as its pencil, and the quiet beauty lies in how reliably the geometry appears time after time, as if the universe enjoys repeating a restful theme. Observers on Earth have followed these visitors for centuries, and with the aid of telescopes on serene mountaintops, they have measured the composition of coma and tail, finding water, carbon dioxide, carbon monoxide, ammonia, and small organic molecules whose presence suggests that comets carry ingredients that were common in the early solar system. The European Space Agency's Rosetta mission, which travelled for a decade to meet the gently spinning body of comet Churyumov-Gerasimenko in the year 2014, watched jets of vapour burst from shadow into sunlight and fade again as the comet rotated and its lander Philae hopped across the surface and settled into a shaded nook where instruments could still taste the air slowly moving from the cold ground. The National Aeronautics and Space Administration sent the Stardust spacecraft to Comet Wild 2 in the year 2004 and gathered airborne dust into a collector of aerogel catching particles as gently as a snowbank receives snowflakes, then returned them to Earth, where laboratory microscopes read their textures and minerals like letters in a book. The Deep Impact mission in the year 2005 nudged a small impactor into Comet Tempel 1 to let cameras watch the interior material bloom into light, and years later, another spacecraft named Epoxy returned to see how the crater had softened, a reminder that even an icy surface evolves quietly from encounter to encounter. These missions turned distant glow into close familiarity, showing that beneath the coma lies a nucleus, with a varied skin sometimes smooth, sometimes rock-like, sometimes cracked into cliffs and pits where volatile ices hide from sunlight, until the comet is near enough for a slow thaw. The redness seen in some surfaces hints at long exposure to solar radiation and to energetic particles which rearrange the carbon in organics into darker, more complex mixtures, while brighter patches may show where fresh frost has been exposed by a collapse or a seasonal shift. The anomalies that invite gentle thought are the varied spin states of comets, and the way outgassing can act like thrusters, altering rotation and even nudging orbits in tiny but measurable ways, so that a visitor's return date must be refined with patience, using each apparition's new whispers of motion. There is also the puzzle of the showering grains a comet leaves behind. Each return loads its orbit with more meteoroids that spread out into a broken ring, and when Earth crosses that ring at the same point in its yearly path, the sky greets a meteor shower, the light of ghostly pebbles burning quietly as they strike the upper air at many tens of kilometers per second and end as streaks that vanish as softly as breath on a window. Over centuries, entire streams thicken and thin, and the slow procession of orbits shifts where Earth meets them, making a calendar of sky events that repeats with comforting regularity, while still offering small surprises. Comets stand in a tender place in the story of water and organics on the rocky planets. Some measurements of hydrogen in cometary water show ratios different from the oceans of Earth, suggesting that comets were only part of the delivery of water to the early surface, and measurements from darker asteroids and their fragments imply that many sources contributed to the blue layer that now covers most of the planet. The calm lesson is that the early solar system shared its resources widely with slow impacts and gentle accumulations over millions of years rather than a single event. Comets also record ancient chemistry from the sunward parts of the birth cloud, and by measuring isotopes in their gases and solids, laboratories can compare that chemistry to meteorites and to planetary atmospheres, a quiet triangulation that builds a picture of origins with each new sample brought home by careful missions. The light of comets, even when seen with the naked eye from Earth, contains stories that would be easy to miss if they were not so persistent. When a bright comet appears near the horizon before dawn or after sunset, it often seems to move little from one night to the next, and this steadiness feeds the restful feeling that the sky's changes are slow enough to accompany sleep. The truth is that its path is a long, thin loop, and for most comets that loop will carry them back into darkness for a time longer than a human life, but a few return often enough to become familiar, like softly recurring notes in a long piece of music. The comet named after Edmund Halley comes back about every 3/4 of a century and has been recorded by many cultures. Spacecraft named Giotto approached it in the year 1986 and watched the night side glow faintly, a hint that evolved organics and tiny particles can scatter sunlight in a way that makes even shadows gentle. Today, surveys that scan the sky nightly find new comets, often, some discovered so early and so far out that astronomers can follow the delicate rise and fall of their activity across many months, learning how a nucleus wakes, breathes and rests as it rounds the sun. The Solar and Heliospheric Observatory, a joint project of the European Space Agency and the National Aeronautics and Space Administration, has watched thousands of small comets skim the sun and fade, tiny visitors that end their journey in a final glow, writes their small chapters into a larger book where every orbit is part of an unhurried library. The quiet speculation is that many more comets wait, especially in the Oort cloud, where the galaxy's tides will from time to time send a new one inward, and that some of these will carry unexpected mixtures of ice and dust, perhaps revealing overlooked pathways from simple molecules to complex ones. Each passage is a reminder that the solar system remains open to fresh arrivals from its own distant outskirts, and that the slow architecture of orbits warmed by a star that rises and sets continues to frame a sky where small wonders appear at a pace kind to the mind. Comets in their serene arcs say that memory can travel, that material can sleep cold and wake warm, and that even brief lights in the sky can carry the restfulness of very long times. Neptune turns in a distant blue twilight where sunlight arrives as a cool wash, and the background of stars feels near, and in that quiet the planet keeps a steady rhythm, a day that lasts about 16 Earth hours, and a year that spans about 165 Earth years, long enough that human lifetimes see only a small arc of its path. The colour that makes Neptune so calm to the eye comes from methane in the upper clouds, which gently absorbs red light and lets blue and green light pass, while deeper within the atmosphere layers of hydrogen and helium carry complex hazes that soften the view into a tranquil gradient. Although the light is faint, motion is not absent, and the winds that circle this world race with speeds of about 2,000 kilometers per hour, the swiftest known in the family of planets. Yet even this speed feels measured at Neptune's scale, because the planet is large, and the currents flow in broad ribbons that follow lines of latitude like patient rivers. A spacecraft sent by the National Aeronautics and Space Administration passed close by in the year 1989 and recorded a dark oval storm near the mid-latitudes that came to be called the Great Dark Spot, a calm abyss of cloud tops where methane ice formed bright white clouds at the edges like gentle surf on a shoal. And years later, when space telescopes looked again, that storm had faded only for new dark features to appear. In other years, a reminder that even in the far reaches, weather can change with a slow grace. The temperature at the visible cloud tops rests near 100 degrees, above absolute zero, cold enough to keep methane as a gas, and to allow crystals of methane ice to condense, yet the planet emits more heat than it receives a quiet surplus from its interior that rises outward and feeds convection, and perhaps this extra warmth helps give the winds their speed and their staying power. The magnetic field carries its own soft puzzle, tilted far from the spin axis and offset from the planet's center, so that as Neptune rotates, the field traces a gentle wobble, creating a magnetosphere that breathes in and out against the solar wind, in a lopsided rhythm, a structure that shows how deep motions in water and ammonia-rich layers may generate currents in ways that differ from the metallic heart of Jupiter or the layered dynamo of Earth. Faint rings encircle Neptune like misty threads, narrow and dark with segments that brighten into arcs, as if grains had gathered into streamers, perhaps guided by nearby moons or by resonances that concentrate particles the way waves collect driftwood along a bay. The rings are not massive. They look fragile, a suggestion that collisions among dust and small stones refresh them from time to time, while radiation slowly grinds the pieces away, and this balance between loss and supply keeps the structures present, but delicate, a softly glowing veil that does not demand attention yet rewards it when seen. The moons form a small court of diverse characters, and among them Triton is the quiet wonder. Triton moves in a retrograde path circling opposite the spin of Neptune, a sign that it did not form alongside the planet but was likely captured from the wider population of icy worlds beyond, and the capture would have been gentle enough or slowed by tidal interactions enough to settle Triton into a stable orbit that still slowly evolves. During that one flyby in the year 1989, the passing spacecraft watched dark streaks rising from the southern latitudes of Triton and drifting downwind evidence of plumes that likely come from nitrogen warmed into gas under a thin glaze of ice, and vented through cracks entraining darker particles that fall back as fans on the pale surface. That surface is a world of water ice, as hard as rock in such cold, decorated with plains patterned like the rind of a melon, with ridges and pits formed by slow freezing and thawing of nitrogen, and perhaps other simple compounds, and an atmosphere so light that its pressure is like a whisper, within a whisper layered with hazes that build from sunlight acting on nitrogen and methane. Triton's polar cap appears bright and clean, a sign that volatile frosts move with the seasons, and over a very long future the moon's orbit will likely decay further until tidal forces either slow it into a tight embrace or pull it apart into a new ring, a far-off possibility that carries no urgency, only a suggestion that even in the outer dark change continues in soft increments. Other moons add their small stories. Nereid travels on a path that is highly stretched so that its distance from Neptune varies widely over a single orbit, and this eccentric journey hints at past gravitational encounters that set the moon on a course that never quite settles into a circle. Proteus is more regular, a blocky dark world close to the rings shaped by slow impacts, and by its own modest gravity into a form that is almost round but not quite so. The smaller shepherd moons with names drawn from river nymphs and sea spirits likely help corral ring arcs and maintain the fragile arcs where particles brighten a dance of tiny tugs that repeats with each orbit and preserves shape the way a metronome keeps time. The peaceful anomaly of Neptune lies in the contrast between its calm colour and its energetic interior, between the faint sunlight and the strong winds, between the vast distance and the vivid meteorology, and the gentle speculation is that deep beneath the clouds at pressures and temperatures where water becomes a supersonic material that can conduct electricity, slow currents arrange the magnetic tilt and set the stage for variations that ripple upward as storms. Another soft question holds in the migration of the giant planets early in the solar system's history. Models suggest that Neptune may have moved outward from the region closer to the Sun, scattering and shepherding icy bodies into the Kuiper belt and into resonant paths, and if this happened gradually it would explain the calm order that we see in some parts of that belt, and the presence of captured worlds like Triton, which would have been delivered by this gentle reshaping of orbits. The winds that roar yet feel unhurried likely draw energy from the planet's inner heat, combined with the stable stratification of the outer atmosphere, allowing jets to persist for years and to reconfigure slowly with the seasons of a year, too long for any one person to witness end to end. When a telescope resolves Neptune as a disk, faint white clouds sometimes appear near the limb, bright methane ice clouds carried by upward flickers in the flow, their edges smoothed by the thickness of the air below, and when those clouds cast shadows or race their own currents, they provide quiet markers that allow the rotation to be measured, a task that is more subtle than it might seem, because the winds slide over deeper layers that turn at slightly different rates. Occultations of stars by Neptune and Triton reveal the transparency and layering of their atmospheres, each event a small and tranquil experiment in which starlight dims in a smooth curve that can be read for temperature and density, and each curve adds to a patient archive that future observers will compare across decades to sense long cycles. In all of this, the planet remains a symbol of serene distance. Its path traces the outer lanes where time stretches and heat thins, and yet it feels connected to the inner worlds through the shared breath of the Sun, through the magnetic web, and through the occasional visitor from the Kuiper belt, whose orbit was tuned by Neptune long ago. The most relaxing truth is that Neptune continues, that its winds keep their roots, that its rings hold their delicate shape, that Triton sighs from its frosts under a distant sun, and that the blue seen through a telescope is not just colour, but a sign of simple molecules working together to create a tone in space that is cool, constant, and kind to the mind. From this vantage, thought can rest on a planet that is both active and untroubled, a distant lantern with a quiet flame reminding the listener that even at the edge order can be gentle and change can be slow. Uranus moves through the outer solar system with a quiet that feels almost ceremonial, a pale world rolling on its side so that its spin axis lies nearly in the plane of its path around the Sun, a tilt of about 98 degrees that turns the rhythm of day and season into a slow and gentle puzzle. Because a Uranian year lasts about 84 Earth years, each pole spends about 2 decades in continuous sunlight and about 2 decades in continuous night, and the ringed equator receives long, low arcs of daylight that seem to slide along the horizon rather than climb high overhead. Methane in the upper air absorbs red light and lets blue and green light pass, tinting the planet a soft cyan that seems to cool the senses before any numbers are known, while deeper layers of hydrogen and helium hold hazes that quiet contrast and leave the disk looking smooth as if it were painted in broad, calm strokes. At the cloud tops, the temperature rests only a few dozen degrees above absolute zero, and unlike its neighbour Neptune, Uranus emits little more heat than it receives from the Sun, an anomaly that invites gentle thought about why its interior appears so reserved. A single passing spacecraft from the National Aeronautics and Space Administration flew by in the year 1986 and found faint rings, a family of moons with diverse faces, and an atmosphere braided with winds that flow along set lanes fast near the equator, and slower toward the poles, with measured speeds that can reach many hundreds of kilometers per hour, yet feel tranquil when seen across a globe this wide. The rings first detected in the late 1970s when the planet passed in front of a star, and the starlight blinked several times. Before and after the main occultation are dark and narrow, made of icy rock and dust that reflect little light, and they appear as fine threads when the ring plane is tilted toward Earth, but nearly vanish when the planet reaches equinox, and the rings turn edge on a graceful reminder that geometry can quietly hide or reveal. Small shepherd moons such as Cordelia and Ophelia are thought to help keep ring particles in line, their gravity sweeping the edges the way careful hands smooth a ribbon, and distant moons like Titania and Oberon move on steady paths while smaller bodies closer in, including Miranda Ariel and Umbriel, present surfaces that speak softly of both calm and upheaval. Miranda shows towering cliffs and oval features called coronar patterns of ridges and grooves that may have formed when the moon warmed from within or was pulled and released by tides, and then froze again, creating patches of terrain that look stitched together by a patient hand. Ariel has bright, fractured valleys where ice seems to have flowed or sagged in ancient time. Umbriel is darker, as if its surface has rested longer under space weathering. Titania and Oberon, larger and farther out, carry broad fault scarps and craters softened by the slow creep of ice. The magnetic field of Uranus adds another quiet puzzle tilted far from the spin axis and offset from the planet's center, so as the planet rotates, the magnetic structure sweeps a lopsided pattern through space, breathing against the solar wind in a rhythm that changes with the long seasons. Auroras have been observed as modest glows rather than dramatic curtains, and they appear to shift with the orientation of this tilted system, a sign that what happens deep within the planet, where pressures turn water and ammonia into unusual states, can shape phenomena at the edge where charged particles meet the air. Scientists picture the interior as layers of water, ammonia, and methane above a rocky core, and at the temperatures and pressures found there, water may enter a superionic form that conducts electricity and helps generate the magnetic field, while carbon deep within could assemble into crystals that drift downward like slow rain of diamond. A thought that is both fanciful and plausible, carried by careful modelling and by laboratory experiments that recreate planetary pressures. The tilted axis itself invites the gentlest speculation of all. One possibility is that in the early days of the solar system, when planetesimals and protoplanets still moved in crowded lanes, Uranus suffered a glancing impact by a body with a mass comparable to that of a large moon, a strike that was strong enough to tip the planet yet slow enough to leave it intact. And if that happened, the energy could have rearranged interior layers in a way that trapped heat or redirected it, leaving the planet today with a subdued thermal glow. Another possibility is that a slow dance of resonances with other giant planets gradually torqued the spin axis over long ages, a process that would also have preserved delicate orbits and allowed the ring system to survive as a thin, persistent structure. Weather on Uranus seems calm when compared with the more dramatic patterns of Jupiter and Saturn. Yet long campaigns with large telescopes on Earth, and with the Hubble Space Telescope, have revealed small bright clouds that come and go, especially near the time of equinox when the sun's light crosses the ring plane, and the changing pattern of illumination may stir the atmosphere. These clouds are likely methane ice condensing where rising motions cool the air, and their drift allows observers to track winds and infer deeper flows. Over the years, careful watching has shown that the winds accelerate and decelerate with latitude, that the southern hemisphere and northern hemisphere can differ, and that features appear seasonally as if the long sweep of sunlight and darkness feeds a very slow cycle that the passing of years will bring into sharper focus. Occultations of stars by Uranus and its moons add to the calm archive of knowledge, each event a smooth dimming and brightening that, when recorded with sensitive instruments, reveals temperatures and densities in the upper air, and the thickness and warp of rings, and when the rings turned edge on in the year 2007, a series of such observations refined the understanding of their shapes and of the small moons that tend them. The 1980s flyby remains the only close visit, and so the planet retains a gentle privacy, but the next decades are likely to see an orbiter and atmospheric probe launched by the National Aeronautics and Space Administration and international partners, a mission designed to study the winds, the rings, the magnetic field and the moons over several years, not to stir but to keep company and to listen. The promise of that listening is a clearer sense of how an ice giant differs from a gas giant and from a rocky world, and of how common such planets might be around other stars, because surveys of exoplanets find many worlds with sizes close to Uranus, suggesting that the quiet, tilted planet may be more typical in the galaxy than Earth or Jupiter. The most relaxing truth that emerges from all this is that Uranus is both unusual and orderly tilted, but consistent, faint, but steady, modest in heat, yet active in pattern, a planet that turns on its side without haste, while rings hold their lane and moons keep their time. The anomaly of low internal heat sits like a soft question that patience can hold without urgency. The magnetic tilt sketches a gentle lopsidedness that repeats with each day, and the seasons teach that light can move slowly and still change everything. From a distance, Uranus looks like a calm bead in the long necklace of the solar system, a pale interval between the strong gold of Saturn and the deeper blue of Neptune, and in its turn it offers a lesson in balance, that a system can be tipped far from ordinary and still achieve a steady grace. In that thought, the mind can ease, imagining a sky under a sun that circles the horizon for years, imagining rings that fade and brighten with geometry, imagining a planet whose very strangeness is restful because it changes on scales that match a lifetime of quiet observation. Saturn turns with a patience that calms the mind, and around it an arrangement of countless icy grains becomes a wide lantern, whose glow changes gently with distance and season, so that the rings brighten and fade as the angle of sunlight shifts, and as the observer's line to the sun becomes more or less direct, a quiet lesson in how simple geometry can paint space with light. A Saturnian year lasts a little less than 30 Earth years, and within that span the planet reaches equinox, when the sun lies in the plane of the rings and the thin sheets almost disappear to distant eyes, then moves towards solstice, when the sun stands above or below the ring plane, and light falls on the grains more directly, carving shadows that give the rings depth, and giving rise to a glow that lifts and settles in a cycle as slow as a long breath. The particles themselves vary from dust motes to boulders the size of houses, yet most are thought to be no larger than small stones and chunks of ice, and together they spread into belts named for letters, in the order they were discovered, with the broad and bright B ring near the middle, the outer A ring beyond it marked by the narrow Keeler gap, and the slighter Encke gap, the inner C ring more diaphanous and ghostly and still closer to Saturn, the very faint D ring, while beyond the A ring a narrow and braided F ring loops like a cord that has been teased and retied. The glow that makes these rings seem like a lantern comes not only from the amount of light that strikes them, but also from how the grains scatter that light. And when the angle between the sun, the rings and the observer becomes very small, the surface shows a gentle opposition surge, a brightening caused by shadows hiding behind particles, and by light paths that interfere less in the backward direction, producing a soft flash that fades as the angle grows again. This effect is stronger in the finer, lightly dusty regions and softer in the denser belts, where particles shadow each other even at small angles, and by measuring the magnitude of the surge at different wavelengths. Thousands of careful observations have quietly revealed the typical sizes and textures of ring grains, a long study carried out by telescopes on Earth, by space observatories, and especially by the Cassini spacecraft that circled Saturn for more than a decade. Cassini, launched by the National Aeronautics and Space Administration, in partnership with the European Space Agency and the Italian Space Agency, arrived in the year 2004 and watched the rings across changing phase angles and across an equinox that came in the year 2009, when the rings grew so thin to the Sun that they almost vanished, and a delicate cobalt light filled the scene. During that season, low shadows drawn by ringlets fell across Saturn's upper atmosphere like perfectly parallel lines, and small vertical warps in the rings became visible as gentle corrugations, suggesting that some past event, perhaps a passing impactor, had tipped the ring plane slightly and sent a bending wave outward that persisted for years. The rings do not sit alone. They're shaped by moons that shepherd edges, clear gaps and stir wakes. Tiny Prometheus and Pandora flit along the inner and outer edges of the F-ring, and tease its strands into braids and knots as their gravity draws and releases particles, while the larger moon Mimas resonates with ring particles in a way that helps carve the Cassini division between the A and B rings, and the little moon Pan turns within the Enki gap like a rounded pebble, keeping a lane open, raising scalloped edges that march beside it in a rippling pattern. Near the outer border of the A-ring, the very small moon Daphnis opens the Keeler gap and stirs scallops and vertical waves that rise like soft dunes of ice, showing that even a minor body can sculpt the sheet when paths align. Over the years, Cassini watched ephemeral spokes glide across the broad B-ring, dark or bright radial features that grow and fade as if dust had become temporarily levitated by an interaction between ring particles, sunlight and Saturn's magnetic field, and these spokes appear more often as the planet approaches equinox, when the Sun lands low on the rings, and electromagnetic forces find their strongest leverage. Fine material from the icy moon, Enceladus thrown into space by south polar plumes of water vapour, and grains spreads outward to feed the wide E-ring far from the main bright belts, and some of that material drifts inward as a slow rain that falls along magnetic field lines into Saturn's upper air, a very gentle loss process that gradually darkens and thins parts of the rings, and that became measurable through the way the planet's ionosphere responded to subtle inflows. The puzzle of age rests over the rings without urgency. Some properties, like their brightness and the relative scarcity of dark contaminants, suggest that the rings could be younger than the planet, perhaps refreshed by the breakup of an icy moon in the last few 100 million years, while other models show that if the rings are massive, they might have endured much longer, with steady recycling of particles masking a deeper antiquity. Cassini's gravity measurements during the grand finale orbits, when the spacecraft skimmed between the innermost ring and the cloud tops, teased out the mass of the rings more precisely, and favoured an intermediate picture, yet left open a gentle range of possibilities that future missions may clarify. Whatever their age, the rings behave like a thin, nearly collisionless fluid, in which countless inelastic bumps and passes create waves at the places where orbital periods match simple ratios with the periods of moons, or with patterns that travel through Saturn's interior. In some parts of the rings, especially the inner C-ring, delicate spiral waves record oscillations deep within the planet, turning the ring sheet into a seismograph for Saturn itself, and allowing scientists to infer how material moves inside the giant, a slow and elegant form of remote sensing that suits the tranquil character of the system. Temperatures across the rings vary with distance from Saturn, with the A and B rings warming slightly in sunlight and cooling into the low 100s of degrees above absolute zero in shadow, and during equinox the shadows stretch and the temperatures dip, altering the stiffness of the ice and changing how quickly certain features relax so that the same lane can show different textures in different seasons. Occultations of stars and of the distant sun by the rings have allowed careful measurements of thickness and density, and they show that the dense B ring, though bright, can be only a few meters thick in many places, a flatness that is soothing to imagine, like a sheet of frost laid across space with almost no wrinkle. The vertical scale is small, the radial scale immense, the azimuthal scale endless, and in that geometry the mind finds rest. The ring plane crossings as seen from Earth, which occur near Saturn's equinox every 14 to 15 years, provide more quiet drama for watchers as the rings slim to the edge and vanish into a line through the planet, allowing moons to be seen more easily and the thin rings to be weighed again through their diminished light. From this long calendar of brightening and thinning emerges the simple, relaxing fact that the rings obey the same gravity and light that everything else does, yet manage to arrange those laws into a visual lullaby. The broader system shares the calm. The North Polar Hexagon, a steady wave that circles Saturn with soft corners, casts a memory of order even when the focus remains on the rings, because the same gentle balance between rotation and atmospheric waves that shapes the hexagon also governs how ring particles align into lanes. The question that rises here is not a sharp one, but a soft curiosity about continuity. How long will the rings keep their current grace? How much new ice will Enceladus add to the E-ring? How slowly will ring rain draw particles inward? How evenly will meteoroid dust darken the grains? And whether the lantern will glow as strongly throughout future seasons as it does now? The calm answer is that change will be slow measured in spans much longer than a human life, while the cycle of geometry repeats in familiar fashion. In this way, Saturn's ring light becomes a companion to rest a steady pattern that can be revisited in memory at any time, a sketch of billions of small ices moving in shared order, scattering sunlight in a chorus that grows and fades with the angle of the sun, the eye and the planet, and leaves a wide bright hush around a world that turns without hurry. Enceladus circles Saturn as a small bright bead, whose southern pole exhales in feathers of ice and vapour, and in that steady breath lies one of the most tranquil wonders of the solar system, a sign that warm water moves beneath a shell of cold. The moon is not large, only about 500 kilometres across a sphere of water ice and rock that reflects so much sunlight that it appears almost pure white, and yet near its south pole 4 long parallel fractures, often called tiger stripes, cut the surface and act as vents, where water vapour and fine grains rise into space in slow, constant plumes. When the Cassini spacecraft from the National Aeronautics and Space Administration arrived at Saturn in the year 2004 and began its close passes, it found these plumes by their backlit glow, and by the way charged particles and dust behave near the moon, and over many years it flew through the spray at varying heights, tasting the chemistry in the vapour and counting the sizes of grains to build a calm, persistent picture of the ocean below. The surface temperature over most of Enceladus sits only a few tens of degrees above absolute zero, but along the tiger stripes the ground glows warmer by tens of degrees in narrow lanes, as if heat from within rises where the crust is thin, and the total heat output from the region is larger than simple models would predict for a world this small and old. The energy source that keeps this area so mildly active likely comes from tidal flexing, the repeated gentle squeezing of the Moon's interior as it orbits Saturn on a path that is not a perfect circle, a shape maintained by a gravitational resonance with the larger moon Dione that keeps the small eccentricity from fading away. As Enceladus moves closer to and farther from Saturn over the course of one orbit, the tiny changes in gravitational pull bend and unbend its rocky core and icy shell, releasing heat that collects most efficiently near the South Pole, where the fractures provide pathways, and that heat lifts water to liquid, mixes it with dissolved salts and gases, and drives it upward through narrow conduits that open straight to the vacuum above. The grains in the plume are mostly high-purity water ice, but mixed among them instruments found sodium, chlorine, carbon dioxide, methane, and larger organic molecules that together point to water that has spent time in contact with rock like seawater, passing through a warm, mineral-rich seafloor. In the vapour itself, they measured molecular hydrogen, a gas that can form when water reacts with iron. Rich minerals at high temperature in hydrothermal systems, and that hydrogen along with tiny silica grains found in the Saturn system that match products expected from hot water cooling, gives a calm confidence that the ocean floor on Enceladus hosts warm vents where stone and water meet and exchange energy and chemistry. The ocean that feeds the South Polar activity appears to be global, or nearly so, lying beneath an ice crust thicker near the equator and thinner near the pole, as shown by how Enceladus wobbles as it rotates, a subtle motion that fits best with the decoupling between crust and core, and by gravity measurements that reveal a distribution of mass consistent with an internal sea. The chemistry gathered by Cassini as it flew through the plume indicates the presence of salts and carbon-bearing compounds, and the distribution of grain sizes suggests that freezing and flash boiling happens in the vents as water moves from pressure to vacuum, a gentle physical process that sorts particles without any need for violent eruptions. The vents themselves pulse, with the orbit opening a little wider when Enceladus is farther from Saturn and closing a little when it is nearer, a breathing that matches the strain of tidal flexing and that changes the rate at which material escapes, so that the moon writes its rhythm across space in a plume that thickens and thins on a scale of days. Much of that material does not fall back, but spreads along the orbit to feed the wide, diffuse ring that lies far from the bright main belts, a halo of fine ice that encircles Saturn and becomes a visible marker of the ongoing activity. And over time, some of those grains drift inward and outward under the influence of sunlight and magnetism in a slow migration that keeps the ring replenished. The South Polar terrain around the tiger stripes shows blue-tinted fractures where fresh ice has been extruded or exposed low ridges flanking the main cracks, built by repeated cycles of opening and freezing rounded mounds, where vents cluster and a field of tiny pits formed by falling grains that return as gentle snow. The landscape carries no jagged violence. Instead, it looks soft like a frozen shoreline where tides have left long lines of frost, and the broad plains farther from the pole are smooth and bright, a sign that fine snow from the plume has draped them in a clean layer that reflects sunlight like a field after a quiet storm. The ocean beneath all this is kept from freezing solid by a combination of tidal heat and insulation from the ice shell, and the pressure at the base of the ice provides a calm lid, allowing thermal and chemical gradients to establish themselves over long periods of time. If the seafloor is rocky, as density measurements suggest, then water can cycle through pores and fractures, warmed by the slow release of energy, as the core flexes and perhaps as radioactive elements decay, giving rise to vents, where temperatures may reach hundreds of degrees above absolute zero hot enough to drive simple reactions, but still moderated by the surrounding sea. In such places on Earth, microbial life finds energy not from sunlight, but from chemistry. And though Enceladus is a very different world, the presence of molecular hydrogen, carbon dioxide, and organic compounds sketches a similar energetic landscape, a place where reactions could proceed gently in the dark over very long times. There is no claim here, only the restful possibility that a small ocean might host the sort of steady gradients that on Earth allow life to persist in calm isolation from the sky. The anomalies that persist are soothing puzzles rather than crises. The total heat output remains little higher than simple tidal models predict, leading to thoughts about layers of soft ice that focus strain, or about a long-lived resonance state that pumps energy more efficiently, or about liquid water percolating in a way that carries heat where it can be released. The exact thickness of the ice shell likely varies with latitude and longitude, thinning near the tiger stripes to perhaps a few kilometers, while thickening elsewhere to tens of kilometers, and that variation could shift with time as the orbit evolves, offering a slow choreography in which vent locations migrate or multiply with no hurry at all. The organic molecules detected include both small species and larger, more complex fragments that hint at polymers, but these fragments are measured in a plume that has already processed material through freezing and explosive expansion, so the original forms inside the ocean remain an open question for patient missions that might one day fly lower and slower, or that might carry a sampler capable of catching larger grains intact. The ring that Enceladus feeds spreads the Moon's story across the Saturn system as a diffuse signature of water and ice, and faint arcs of material can be traced to other moons that intersect the ring, showing that the gifts of the plume continue outward to places that will never see the tiger stripes directly. The long arc of observation by Cassini created a record that stretches across seasons, including a time when the sun stood low over the southern hemisphere and carved long shadows from ridges and vents, making it easier to measure heights, and to watch how the brightness of fresh frost changed with days and weeks, and these changes played out not as sudden shifts but as gradual drifts that mirror the slow heartbeat of the plume itself. The most relaxing truth is that Enceladus keeps going a small moon that holds a warm sea under a cold sky, breathing through fractures that glow faintly in the infrared and scatter sunlight in backlit fans, a place where the ingredients for chemistry circulate and where water, salt rock, and time meet in a very gentle workshop. The quiet question that follows is simple and expansive. How long has this ocean turned? How far beneath the crust do vents reach? How many other moons keep similar secrets with their own rhythms and temperatures? The answers will come in years and decades, carried by future orbiters and plumes that go on rising. But no urgency is needed because the scene changes slowly, and the moon seems content to continue its soft work while we listen. In that thought, Enceladus becomes a cradle of calm curiosity, a lantern under the rings that burns with the mild light of scattered ice, and the deeper glow of heat from tides, steady enough to soothe and mysterious enough to gently widen the mind. Jupiter turns like a grand banded lantern, a world so large that more than 1,000 Earths could fit inside, yet it rotates in only about 10 Earth hours, drawing its atmosphere into steady jets that encircle the planet as clear belts and pale zones. The colours and textures that appear to a telescope are the result of simple ingredients arranged in layered calm ammonia crystals at the highest visible cloud tops, with water clouds deeper below, and a mixture of sulphur and other compounds that sunlight and lightning slowly reshape into gentle browns, creams and soft reds. The darker belts are lanes of sinking air, where the tops of clouds lie lower and warmer, allowing glimpses into deeper layers, while the bright zones are regions of rising air where ammonia ice condenses into high reflective sheets. The pattern looks fixed to the eye, yet within it everything flows with jets that alternate eastward and westward from the equator to the poles, each jet a long river of air whose surface carries ovals, festoons and waves that drift and reform at a tranquil pace. The great red spot sits within this order as a vast, long-lived storm, an anticyclone larger than Earth that has persisted for centuries while quietly changing its shape. Its colour and its size and recent measurements suggest that it is slowly shrinking, becoming more compact while its winds remain swift, and its ring of surrounding currents maintains a graceful swirl that holds to a repeating rhythm. Lightning flickers within the deeper clouds where water carries charge through collisions of droplets, grauple and ice, and the flashes recorded as gentle radio signatures reveal tall towers of moist convection that rise from far below, bringing heat and chemistry upward, as if the planet breathed through giant slow lungs. In the year 2016, the Juno spacecraft from the National Aeronautics and Space Administration slipped into a polar orbit and began to map the planet's gravity, magnetism, microwave glow and auroras, and the portrait it has gathered shows that the familiar bands seen at the cloud tops extend downward for thousands of kilometers before easing into a more uniform interior, a discovery that anchors the visual beauty to a deep and steady structure. Juno's microwave instrument senses ammonia and water beneath the visible clouds and reveals columns that vary with latitude and season, including an ammonia pore belt near the equator, where sinking motion carries the gas downward, and richer plumes elsewhere where it rises, painting a gentle three-dimensional view of circulation. At the poles, Juno's camera revealed something earlier missions could not see: well-organized arrays of cyclones, packed like petals around central polar storms, 8 in the north and 5 in the south. Each storm shaped by the balance between rotation and pressure so that they move little relative to one another, a pattern that appears stable over many years, and that adds a quiet symmetry to places once thought chaotic. The magnetic field of Jupiter is powerful and unusual, with a tilted and offset dipole, and a patch of intense localized field near the equator, nicknamed the Great Blue Spot in magnetic maps. And as Juno measures changes over time, it sees a slow drift in the field that hints at winds and conducting layers moving beneath the clouds, perhaps where hydrogen becomes metallic under great pressure and carries electric currents that feed the dynamo. The auroras near the poles shimmer in ultraviolet and infrared light, driven both by the solar wind and by the flow of charged particles from the volcanic moon. Io, which releases sulfur and oxygen into a torus that encircles Jupiter and supplies energy to the magnetosphere, and when those particles slide down magnetic field lines into the upper atmosphere, they light the ovals with constant rippling arcs. The calm puzzle of lightning at high latitudes where sunlight is weak and temperatures are colder led to a picture in which small ammonia-rich hailstones, sometimes called mushballs, form and fall, carrying ammonia and water downward and helping to explain why ammonia varies so strongly with depth and latitude. The result is a gently circulating cycle of evaporation, condensation, and precipitation that operates in a way both familiar and strange compared to weather on Earth. The Galileo probe that entered Jupiter's atmosphere in the year 1995 measured surprisingly dry air in the region where it fell, likely a local hotspot where sinking motion suppressed clouds, and for years that reading stood as a quiet anomaly now softened by the broader view from Juno and from Earth-based observations that show water and ammonia are plentiful in other regions, though distributed unevenly. The snow-white bands near the equator sometimes produce long, pale plumes that curl into delicate waves as they ride faster currents and farther from the equator. The belts become segmented by chains of small white ovals and brown barges. Each feature a slow whirlpool that can last for months or years before merging or fading, and in the southern temperate latitudes pairs of storms have been watched to approach and combine into a single larger oval, an event that plays out on scales that feel unhurried against the planet's fast rotation. The vertical structure of the atmosphere shows layers that couple and decouple as conditions change. Where rising motion brings ammonia upward, thin high clouds form and cast soft shadows on lower layers, and where descending motion dominates the air becomes clear and allows deeper reddish clouds to be seen, and in both cases the temperature gradient and the presence of phosphine, a trace gas that indicates vertical mixing, act as clues to the depth of motion. Waves called Rossby waves and Kelvin waves propagate within and between bands, shaping meanders and acting as natural metronomes that organize cloud features without abruptness. And sometimes the equatorial zone undergoes a quasi-periodic shift in brightness that echoes a longer rhythm observed on Earth in the stratosphere, suggesting that even in such a different atmosphere, gentle cycles can arise from the same basic physics of rotating fluids. Jupiter also wears a faint ring system made of dust shed by small inner moons, a narrow, dim halo that reflects only a little sunlight, and that reveals itself best when seen at wide angles, reminding the viewer that even this giant carries delicate adornments, in addition to its bold bands. The planet's year is almost 12 Earth years, and over that span the Sun's light angle across the atmosphere changes, slowly modulating the heating of different latitudes, and introducing a mild seasonality that can be traced in the shifting strength of jets and the frequency of storms. Yet the most striking impression remains one of constancy within change, for the bands hold their lanes, and the major currents keep to their tracks while the details drift and renew. The Great Red Spot, though smaller today than when measured a century ago, still towers above surrounding clouds by many kilometers, and spins with winds that circle in less than a day, trapping darker material that gives it color, and generating acoustic and gravity waves that ripple outward across nearby belts. Peels of reddish flakes sometimes shear from its edges and stream downstream, painting the belts with faint tints that fade with time. Sounding of gravity during close passes shows that the spot's roots extend deeper than the highest clouds, and thermal measurements show a cool center and a warm edge consistent with its broad, stable rotation, a structure that is both dynamic and restful in how it repeats its form pass after pass. The restful speculation that follows from all of this is that Jupiter's bands and storms are the visible face of deep, slowly evolving circulations that tap the heat left from formation and the steady sunlight above, and that the planet's magnetic field and auroras respond in kind, pulsing to rhythms that connect the clouds, the conductive interior and the space around it as one calm system. Over decades to come, Juno will continue to adjust its orbit and send back data and giant telescopes on Earth, and in space we'll keep watching the belts brighten and darken, the white ovals merge, the red spot breathe, and the polar storms hold their flower-like rings. The gentle question that remains is not whether any of this will end soon, because these patterns are robust, but how the slow cycles nest within one another for centuries, how deep winds trade momentum with the interior, how lightning and mush balls tune the ammonia budget, and whether the colours that lull the eye are set more by sunlight above or by chemistry brought up from below. The most relaxing fact may be that Jupiter offers a living mural that changes enough to reward attention, yet keeps a composition that endures a broad harmony of zones and belts, ovals and waves, light and shadow, all arranged by gravity and rotation into a scene that invites the mind to drift, knowing that when it returns, the bands will still be there, flowing in place under the steady light of a distant sun. Europa moves in a steady path around Jupiter, keeping the same face turned toward the giant, so that one hemisphere always looks inward and one always looks out. And in this gentle lock the moon flexes with each orbit, as the pull of Jupiter and the tug of neighbouring moons shift slightly in a rhythm that never hurries. The surface gleams as a nearly unbroken sheet of ice bright enough to reflect most of the faint sunlight that reaches the Jovian system, and across that shell run long dark lines that intersect and drift, a crosshatch of fractures and paired ridges that suggest the ice has opened and refrozen many times. The temperature at the surface lies only a few dozen degrees above absolute zero, cold enough to make water ice as strong as stone. Yet the pattern of cracks and the rounded blocks of chaos terrain speaks softly of motion, as if warm water has once reached near the surface and weakened the crust before freezing again in a slow, careful process. When the Galileo spacecraft from the National Aeronautics and Space Administration passed through the Jovian system in the late 1990s and early 2000s, its magnetometer sensed a field that was not fixed, but induced a response to Jupiter's rotating magnetic environment that could only be explained if a conductive layer existed beneath the ice, and the simplest conductor, there would be a global ocean of salty water. Additional hints came from the way the surface absorbs and reflects infrared light with spectra that suggest hydrated salts mixed with ice, and from images that show places where ridges rise as paired walls, separated by a central lane, shapes that on Earth can form when ice splits and brine or slush wells up to fill the gap before freezing. The ocean implied by these strands of evidence is likely deep, perhaps tens of kilometres to more than 100 kilometres thick beneath an ice shell that may range from only a few kilometres in some regions to several tens of kilometres in others, and it rests above a rocky mantle that could host chemical reactions where water meets stone. Tidal heating supplies the gentle energy that keeps the ocean liquid. Europa participates in a three-body resonance with neighbouring Io and Ganymede, a pattern in which for every orbit of Ganymede the Moon, Io completes 4 and Europa completes 2, and this regular gravitational handshake maintains small elliptical paths that cause Europa to flex as it moves closer to and farther from Jupiter. That flexing releases heat within the interior most strongly in layers where ice and rock respond by bending, and the heat rises toward the base of the shell, making a warm boundary where new ice can form, and where pockets of liquid might collect and slowly travel upward along fractures. The surface shows few large impact craters, a sign that geologic renewal has erased many ancient scars, and that the shell, though cold and strong at the top, can move over long times. Chaos terrain appears as rafts of broken plates rotated and shifted against one another amid a granular matrix, a landscape that may form when a lens of water or brine melts into the lower shell and lifts blocks before draining or refreezing, leaving a soft record of buoyancy and gentle disorder. Reddish colours along some ridges and bands hint at materials later altered by radiation from Jupiter's magnetic field, which sweeps charged particles across Europa's surface and splits water molecules into lighter gases that escape and oxidants that remain, creating a tenuous atmosphere rich in oxygen that hangs as a near vacuum above the ice. Those oxidants can slowly work their way downward through fractures and pores, potentially mixing into the ocean and providing a steady, quiet source of chemical energy. In the years after Galileo telescopes in Earth orbit and on the ground added to the picture by watching the limb of Europa for transient features, the Hubble Space Telescope recorded narrow plumes of water vapour on several occasions, when Europa crossed in front of Jupiter, seen as brief localized absorptions against the bright backdrop, and a later reanalysis of a close Galileo pass showed a magnetic and plasma signature consistent with a spacecraft flying through a thin plume. These hints suggest that Europa may sometimes vent small amounts of vapor through fractures not in tall geysers like those of a strong volcanic world, but in modest breaths that lift a few hundred kilometers into space before falling back as frost. If such vents are intermittent, they could be tied to the small changes of stress, with the orbital position opening a little wider when tides pull and closing when tides push, creating a gentle cycle that persists for many years. The ice shell itself may experience a form of slow, icy tectonics. Along some long lines, the two sides appear offset as if the surface has faulted and slid. Elsewhere, entire plates seem to have rotated by many degrees relative to their surroundings, and in a few regions, bands of young ice offer stripes that resemble mid-ocean ridges on Earth, in outline though formed by far colder materials and by the quiet freeze of brines rather than by molten rock. Double ridges, the most common raised features, might arise when water pockets within the shell press upward and fracture the overlying ice, then freeze and expand to lift paired walls, while a central trough accumulates refrozen frost, a process that could repeat many times to build heights of tens to hundreds of meters in a rhythm that keeps time with tides. The interior ocean, if it touches a rocky floor, could host warm vents, where water leaches minerals from stone and returns them to the sea, a scenario supported by measurements of induced magnetic response that fit best with salty brines, and by detections of simple organics and sulfur compounds in the surface ice, that may be products of both radiolysis at the top and water-rock interaction below. Laboratory studies and models show that under Europa's pressure and temperature conditions, different forms of ice can exist, including phases that sink or float depending on salinity and heat, and this could drive slow overturn that mixes the shell and carries surface oxidants downward. The gentle energy budget of the Moon allows processes to linger. Heat diffuses from the base of the shell toward the surface over centuries. Fractures propagate and then heal over decades. Brines refreeze along vein networks in patterns that might be revealed by radar in future explorations. The quiet anomalies that remain encourage patient curiosity. The thickness of the shell varies in different studies, with some models favoring a thinner, more active lid, and others a thicker, more insulating one, and the truth may be a patchwork where tidal dissipation concentrates stress and thinning in bands that migrate slowly over time. The possible plumes appear in some observations and not others, hinting that they may be episodic faint and tied to small conditions that are hard to predict. The reddish materials have spectral signatures that can be read as sulfuric acid hydrates or as salts such as sodium chloride altered by radiation, and both interpretations may be right in different places, implying a varied chemical story whose details will require closer, longer looks. In the coming years, missions will make those looks possible. The Europa Clipper mission from the National Aeronautics and Space Administration is designed to fly past Europa many dozens of times, carrying ice-penetrating radar to sound, the shell magnetometers to refine the ocean's depth and salinity infrared, and ultraviolet spectrometers to map composition, and cameras to catch active plumes if they appear, while the Jupiter Icy Moons Explorer from the European Space Agency will tour the Jovian system and later orbit Ganymede, gathering complementary readings of fields and surfaces that will place Europa's behavior in a wider context. Together they will listen for the ocean by tracing how Europa responds to Jupiter's fields, will measure the smoothness and roughness of the shell, and will sample the very thin atmosphere for water and salts that rise from below. None of this seeks to hurry the moon because the moon moves at its own pace, guided by gravity and cooled by distance, and the best approach is to keep a long watch that lets slow cycles reveal themselves. The most relaxing truth about Europa is that it keeps its ocean quietly beneath a shell that records tides as long curving lines, and that sometimes loosens its grip to breathe out a little vapour into a near silent sky. That ocean is not a stormy place by human measure. It is dark insulated and lightly stratified with gentle currents driven by heat from below, and by freezing and melting at the boundaries above and below, a calm circulation that could last as long as the resonance holds, and the interior continues to flex. The questions that follow are not urgent but welcoming. How thick is the ice where the ridges are highest? How salty is the water? How often do the vents sigh? How far do the oxidants travel from the surface to the sea? These are the kinds of questions that can accompany rest because their answers will take time, and because each new piece will fit into a picture that is already soothing in its broad outlines. Europa, with its bright crust and quiet cracks, reminds the mind that even under cold and distant skies, warmth can gather out of rhythm and pressure, and that beneath a still surface an entire ocean can turn in peace. Ganymede moves in a calm path around Jupiter, and carries within it a gentle surprise, a magnetic field of its own that wraps the moon in a small magnetosphere, a cocoon nested inside the larger magnetosphere of the giant planet, so that a shield lives within a greater shield, and the flow of charged particles must thread 2 layers before touching ice and rock. This quiet strength sets Ganymede apart, for it is the largest moon in the solar system, wider than the planet Mercury, with a diameter a little more than 5,000 kilometers, and yet it is not a planet in its own right, but a companion that keeps time with the resonant dance of the Galilean moons. The surface is a tranquil mosaic of 2 broad terrains. Darker, older regions hold the record of countless small impacts and ancient processes, and lighter, younger regions are cross-hatched with long, bright grooved lanes that run for hundreds of kilometers, as if ice once rose, stretched, and settled into ordered wrinkles. The temperature at the surface sits only a few tens of degrees above absolute zero, but the interior, warmed by long-stored heat and by a modest share of tidal energy from Jupiter's pull, appears layered into an outer shell of ice, a deep ocean of salty water, high-pressure ices beneath that ocean, and a rocky mantle over a metallic core. It is in that core that slow motions of liquid iron, or iron mixed with sulfur, likely generate the magnetic field, a gentle dynamo that has persisted over geological time, and that announces itself through the way Ganymede interacts with the moving plasma of Jupiter's environment. When the Galileo spacecraft from the National Aeronautics and Space Administration explored the Jovian system in the late 1990s, instruments detected a magnetic signature that could not be explained by induction alone, showing that the field had a permanent component, and magnetic lines near the equator opened and closed in ways that suggested miniature auroral ovals could form where charged particles spiral into the thin atmosphere. Later observations with the Hubble Space Telescope recorded a subtle rocking in bands of atmospheric glow at ultraviolet wavelengths, a motion that fits best if a salty ocean lies beneath the ice, and conducts currents that partly screen Jupiter's changing magnetic orientation, so that Ganymede tells 2 stories at once, a metallic heart that makes a field and a buried sea that carries induced currents of its own. The ocean itself is inferred to be tens to perhaps more than 100 kilometers deep, depending on latitude and chemistry, with salinity high enough to conduct electricity and density enough to float beneath an upper ice shell of uncertain but probably tens of kilometers thickness. Under the pressure there, water can adopt high-pressure ice phases that are denser than liquid, and that may stack in layers between the ocean and the rocks, below a quiet arrangement that complicates the question of whether water touches rock. Yet models allow regions where warm plumes rise, and high-pressure phases thin opening pathways that could carry minerals upward, or allow brines to gather. The grooved terrain on the surface hints that in the past the shell experienced tension that opened fractures and allowed warmer ice from below to well upward in slow, ductile flow, creating ridges and troughs that run in parallel sets, then crossing each other in gentle grids. Craters look subdued in some of these belts, softened by the creep of ice over time, while in the ancient dark fields they remain sharper and more numerous, recording a longer, quieter exposure to the rain of small impactors that has touched every solid surface in the outer system. In polar regions, charged particles guided by Ganymede's field can precipitate into the atmosphere and onto the ice, creating faint auroras and altering surface chemistry in circles that ring the poles, and those circles drift in response to Jupiter's wider field, giving observers a metronome for the ocean screening effect. The magnetosphere within a magnetosphere creates a layered dance with multiple boundaries. Upstream of Ganymede plasma carried by Jupiter's rotation meets the Moon's field and forms a bow wave, while downstream a long soft tail of magnetic lines stretches away, and within the near environment there are reconnection events where lines break and join, releasing energy in modest pulses. Yet even this electromagnetic weather feels measured at Ganymede's scale, repeating in patterns that hold for many orbits. Juno, the spacecraft now in polar orbit around Jupiter, has flown near Ganymede and refined the picture of its field and of its gravity, confirming a dense core and layering consistent with a deep ocean, and recording how the small magnetosphere floats within the large, a configuration unique among moons. The thin atmosphere of Ganymede is made mostly of oxygen molecules, created when sunlight and charged particles split water ice, and allow the lighter hydrogen to escape, leaving oxygen that pairs up and gathers near the surface, at pressures far lower than those of a good laboratory vacuum, and this gas can freeze into ozone in the ice, a marker the instruments read as a faint hue when the light is right. Over the long calendar of its orbit, Ganymede remains tidally locked, showing the same face to Jupiter, and the leading side that meets dust head-on carries a slightly different patina than the trailing side, a subtle asymmetry, seen in many moons that sweep through ring and dust environments. The dark material that darkens some terrains may include carbon-rich compounds and iron-bearing grains implanted by micrometeoroids and by radiation, and over time the ice beneath relaxes, rounding edges and keeping the profile smooth. The quiet mystery of the grooved belts invites a few gentle possibilities. They could mark places where the shell once rotated slightly, relative to the interior, a process called true polar wander, lifting and lowering stresses that then withdrew. They could be the frozen signature of global expansion, if the inner layers warmed and expanded, or if liquid water migrated and refroze in new arrangements stretching the outer shell. They could also be guides to tides aligned with patterns where small differential stresses repeat, and over ages accumulate into kilometre-scale structures without a single sudden event. Each idea speaks to slow change and to a moon that can store and release energy softly through ice that flows on timescales much longer than human experience. The presence of a deep ocean suggests exchanges between surface and interior, though the path is likely indirect and unhurried. Salt seen in spectra along some bright bands hint that brines once reached near the surface, or that cracks allowed materials to be concentrated by repeated frost and thaw within the shell. And if oxidants created at the surface by radiation, do find a way downward, they could alter the chemistry of the ocean in ways that increase its capacity to host slow reactions at the base of the ice. In the coming decade, the Jupiter Icy Moons Explorer from the European Space Agency will orbit Ganymede and fly by Europa and Callisto, carrying radars to sound the shell, magnetometers to trace the field, and spectrometers to map ice and salts. And it will linger long enough to watch the auroral bands drift, and to time their motion against Jupiter's changes, a prolonged listening that suits the Moon's pace. The National Aeronautics and Space Administration's Europa Clipper, while focused on Europa, will add context for Ganymede's environment and field, and together these missions will refine how the inner magnetosphere shapes the flow of plasma, and how the ocean's conductivity varies with depth and latitude. Through all of this, Ganymede's most relaxing truth remains the layered shelter. It offers a magnetic blanket inside a larger magnetic blanket, an ocean under ice, a field around stone, and water, an arrangement of protections that says stability can be built in nested forms. The soft question that follows is how long this arrangement will endure, how the dynamo will age, whether the ocean will thicken or thin, whether grooved bands will ever seed new belts, and how often polar light circles will shimmer in response to the wider field. None of these invite haste. They are questions fit for long seasons and for missions that return for instruments that watch, and find the same patterns again with small variations that help the picture come into focus. In imagining that view, one can rest on the idea of a moon that keeps its own compass steady, while moving through a larger compass field, a serene body that holds both memory and motion in a balance that endures. Between Mars and Jupiter, a broad band of small worlds turns in quiet lanes, and the space among them is far wider than pictures once suggested, more like a sparse meadow than a crowded field, a region where gravity and sunlight set a slow choreography that has lasted since the solar system was young. This is the asteroid belt, and within it the dwarf planet Ceres moves, with a calm that hides soft activity beneath a pale surface. Ceres is nearly 1,000 kilometers across, large enough for its gravity to pull it into a round shape, and its crust carries hydrated minerals that point to water long involved in its history. When the spacecraft Dawn from the National Aeronautics and Space Administration arrived in the year 2015, after a first stop at the large asteroid Vesta, it found bright patches on Ceres that gleamed like frost against darker terrain, most famously inside a wide basin named a crater, where a central pit called Cerealia Facula and scattered patches called Venalia Faculae reflect sunlight as if polished. The brightness comes from salts, mainly sodium carbonates, left behind when brines reached the surface, and water evaporated into the thin exosphere, and the sharp edges and crisp textures of these deposits suggest that some activity continued into the recent geological past, rather than ending billions of years ago. Nearby rises a solitary dome called Ahuna Mons Broad, and gently sloped, whose flanks show streaks of bright material, and whose shape resembles a cryovolcanic construct, a mountain raised by slowly rising salty water, rich slush that froze as it spread, a tranquil reminder that cold volcanism can shape a dwarf planet with no need for fire. Gravity mapping and the motion of Dawn in low orbits revealed that Ceres likely holds a deep interior that is not fully solid, with a crust that contains water salts and clays over a mantle that may remain weak or partly mobile, and the distribution of mass fits with the idea of a brine reservoir lingering at depth beneath a crater. Telescopic observations made before Dawn's arrival had already seen short-lived emissions of water vapor from localized regions on Ceres detected as faint signatures against the black sky, and the spacecraft's close studies add a calm confidence that brine can still move slowly through the crust and reach near the surface through fractures opened by impacts or by the long, gentle recoil of cooling. Away from Ceres, the belt holds bodies with many stories. Vesta Dawn's first destination in the year 2011 is smaller than Ceres but denser, and more rock-rich, with a basaltic crust and a huge basin at its south pole, carved by an ancient impact whose rings and central mounds look like frozen waves and meteorites found on Earth called Howardites. Eucrites and Diogenites match its composition, linking a world to stones that can be held in a hand. Other asteroids carry moons of their own small companions bound by gravity into quiet pairs. One such body named Ida was seen by a passing spacecraft with a tiny moon Dactyl circling closely, and many more binaries have been found by radar and by careful light curves that show the body and its partner taking turns to affect the brightness. The belt is structured by the distant influence of Jupiter, whose gravity carves gaps at orbits, where periods make simple ratios with the giant planet, leaving Kirkwood gaps that mark places where repeated tugs slowly pulled bodies into new lanes. Between these gaps drift families of asteroids that share similar orbits and surface colors, likely fragments of ancient parent bodies disrupted long ago, their pieces rounding and darkening over millions of years, as sunlight and micrometeoroids smooth sharp edges. The quiet force of sunlight itself plays a role in the long view for the Yarkovsky effect. A subtle push arising because a rotating body re-radiates heat unevenly from day side to night side can make small asteroids drift inward or outward by tiny amounts each year, and over millions of years this drift can carry them into resonances that deliver them to planet-crossing orbits and eventually to Earth's neighborhood. In this way, fragments from the belt become meteorites that fall into deserts and onto ice sheets and laboratories, find in them preserved textures of the early solar system chondrules that once floated as molten droplets, matrix grains that hold carbon compounds, water-altered minerals that record low-temperature chemistry, and metals mixed with stone that speak of early heating and cooling in small evolving worlds. Some of the belt's members have surfaces rich in carbon and hydrated minerals that speak to early alteration by water, and these bodies are kin to the near-Earth asteroids that Japan Aerospace Exploration Agency and the National Aeronautics and Space Administration have visited for sample returns. The spacecraft Hayabusa 2 from the Japan Aerospace Exploration Agency travelled to the small world Ryugu, a dark rubble pile body shaped like a spinning top, and in the year 2020 it delivered grains to Earth that contain carbon-bearing compounds, water-bound in minerals, and delicate organics preserved since the dawn of planet building. The spacecraft OSIRIS-REx from the National Aeronautics and Space Administration visited the asteroid Bennu, another dark rubble pile, and in the year 2023 it returned samples that include abundant carbon and hydrated minerals, soft powders and pebbles that echo the chemistry inferred across many carbon-rich asteroids, and that frame a gentle picture. Water and organics were common, and time works slowly to alter them in countless small worlds. The belt also carries dust released by collisions and by the steady grinding of particles, and that dust spiraling inward under the gentle drag of sunlight contributes to the zodiacal light that can be seen from Earth as a soft, triangular glow before dawn and after dusk, a sky sign that the belt's quiet recycling never really stops. Temperatures in the belt vary with distance from the sun, but often lie far below the freezing point of water, cold enough to preserve ice in shaded places, and within deeper layers, especially on larger bodies where heat leaks slowly. Ceres shows patches near high latitude crater walls where water ice lies exposed in shadowed spots, and spectral maps reveal hydrated salts and clays that formed with water and now rest like gentle testimony that water once moved through the crust. The exosphere of Ceres is insubstantial, a whisper of gas that gathers when sunlight frees molecules from frost, or when impacts lift volatiles into flight, and it disperses quickly, giving no pressure to shape weather, only a hint that the dwarf planet breathes in a very slow way. The belt as a whole has only a small fraction of the mass needed to make a planet perhaps less than 1/20th the mass of the Moon, and the reason lies in the early presence of Jupiter, whose gravity stirred the region and kept bodies from easily merging so that instead of one large planet, the belt preserved a population of small to mid-sized remnants, each with its own path through billions of years. The calm puzzles that remain are pleasant to hold. How recently did brines rise within a crater to leave salt that is still bright? How deeply does the cryovolcanic root of a Hunamons extend, and how often did such domes form? How does the slow push of sunlight and the nudge of resonances distribute small bodies among families over tens of millions of years? Why do some surfaces keep fresh frost, while others wear a uniform patina of darkened dust? The answers are already partly in hand, and will continue to arrive in the same unhurried cadence. Radar on Earth refines the spin and shapes of many bodies. Infrared spectra from space telescopes trace hydration and organics. Occultations of stars by asteroids are timed by observers across continents to measure sizes and to reveal when a moon passes beside its parent as a second shorter blink. Missions now returning and missions to come will place more grains and small stones into laboratories where microscopes will read their layers like tree rings and compare salt chemistry to what Dawn saw on Ceres. The most relaxing truth about the belt is that it is both a museum and a workshop preserving the earliest textures of planet making, while still processing them gently through small impacts, thermal cycles and slow drifts with no rush and with no single event commanding the whole. In this gentle space, Ceres stands out as a calm centre, a world that keeps water bound in minerals, and perhaps still moves brine along fractures to paint bright salt upon a dark floor, all under a sun that warms enough to drive subtle change, but not enough to erase the memory of the deep past. The questions that rise at the end of this view are quiet ones. How many other cryovolcanoes are hidden by time on Ceres? How do buried ice layers endure inside smaller asteroids? And how the zodiacal dust that drifts through twilight each evening renews itself, with a balance so steady that it can soothe the eye year after year. Mars turns under a pale sky with an atmosphere so thin that sound carries poorly, and wind sculpt sand with patience, and in this quiet place frost and breath play out in cycles that last the length of a Martian year, a span nearly twice that of Earth, with seasons that linger and leave gentle traces. At dawn in winter, carbon dioxide, the main gas of the air, condenses on the ground, as frost-painting dunes and rocks with a thin white that shines for a short while before the sun lifts it back into vapour, and at the poles this same process grows caps of bright ice that expand and retreat with the season laying down, and erasing layers that record the rhythm of light like rings in a tree. Water ice hides beneath dust in many regions, and at high latitudes it lies close enough to the surface that a small scoop would find it just under the skin, kept stable by cold air and the protection of soil grains. Cameras flown by the National Aeronautics and Space Administration and the European Space Agency have watched these frosts appear and fade, and infrared instruments have measured their temperature and thickness, finding that the carbon dioxide frost can come and go in a single night, while water frost lingers more in shade and on slopes that face away from the sun. When spring arrives at the poles, sunlight penetrates the translucent seasonal ice and warms the dark ground below, causing carbon dioxide trapped near the base to sublimate into gas that builds pressure and vents, through weak spots sending dark fans of dust across the surface that form patterns like gentle brushstrokes, a process sometimes called the spiders for the branching channels it leaves. The air itself is a soft breath. It is only a fraction of Earth's surface pressure, composed mostly of carbon dioxide, with a trace of water vapor and nitrogen, and it grows and shrinks as carbon dioxide moves from sky to ground and back, changing the pressure of the whole planet by a few tens of %, with the seasons a deep inhalation and exhalation linked to polar light. The winds that flow across this thin air pick up grains of sand and carry them in hops called saltation, moving dunes downwind by small amounts each year, while dust finer and lighter can be lifted into the sky to form hazes and storms that dim the sun and settle slowly as a faint veil over plains and hills. The Mars Global Surveyor in the late 1990s and early 2000s, the Mars Reconnaissance Orbiter since the year 2006, and other orbiters have watched dark slope streaks appear and widen on dusty slopes after storms, as if the surface had been brushed clean by the passage of wind or by the flow of grains, and sometimes bright frost deposits mark the first mornings of winter along crater rims, telling a story of atmosphere and ground that whisper to each other through temperature. In the year 2012, the rover Curiosity arrived in Gale Crater, where layered rocks rise in a mound named Mount Sharp, and its instruments have measured the daily and seasonal breathing of methane at a level of parts per billion, a faint signal that ebbs and flows with air stability, and perhaps with temperature at the surface, a soft mystery that does not demand a single answer. The rover Perseverance, which landed in the year 2021 in Jezero Crater, rests near deltas of ancient sediments that preserve the memory of rivers that once flowed when the air was thicker and water was liquid at the surface for longer spans. And even now, in the present cold and dryness, frost still finds its way onto rock and sand in the early morning, then leaves without a trace by midday. Nighttime humidity rises as the air cools and frost nucleates on small grains, sometimes bonding them lightly until sunlight frees them, a process that helps set the texture of sand and dust, and that can make slopes more stable for a few hours, then looser once more. In mid-latitudes, patterns called polygonal ground appear, where ice just below the surface expands and contracts with temperature over many seasons, cracking soils into gentle geometric tilings that echo patterns in permafrost regions on Earth, and in some craters, layered deposits form domes and scarps, where ice is exposed by erosion clean and bright in cross-section, like a cut through a layer cake of winters. Water vapor, though scarce, cycles with the season in ways that sound restful when written as numbers that return again and again, more vapor in southern summer, less in winter, with the planet's tilt and orbit, shaping how much sunlight touches each pole and how much water escapes to the upper atmosphere, where it can be broken by light and where hydrogen can drift away to space. Early in Mars history, the air was thicker and the climate allowed rivers and lakes to persist, as shown by the branching networks of valleys that cut across highlands and by the deltas that sit at the mouths of crater lakes. But today the signatures of flowing water are transient and gentle, controlled by frost, by thin films of brines in the rarest conditions, and by the slow creep of ice in glaciers that hide beneath dust mantles. Radar from orbit has traced these buried glaciers as streamlined features that retain shape, while covered by insulating fines and surface features such as lobate debris aprons and lineated valley fills reveal flow over spans of time measured in hundreds of thousands of years, as the planet's tilt wobbled and moved ice toward or away from the equator in very slow climate cycles. The polar layer deposit stacks of ice and dust laid down over millions of years keep a pale history of these cycles. They're layers like thin pages that can be read by radar and by high-resolution images, where erosion has cut windows into the stack. Within them lie variations in dust content and grain size that mark times, when the air carried more or less fine material, and when frost stayed longer or shorter at a given latitude. Dust storms that grow from local gusts to planet-encircling events occur in some years, especially when southern spring and summer direct more sunlight onto the southern polar cap and set strong temperature contrasts. And during those years the sky turns amber and the daily temperature range narrows as dust absorbs sunlight and warms the air aloft while shading the ground. Rovers have watched such storms arrive as a gradual dimming rather than a sudden wall dust. Devils have traced their paths in graceful columns that leave dark tracks by removing fine, bright coatings, and when calm returns, frost can again take its place on cold mornings, as if the atmosphere had simply paused before returning to its slow routine. Instruments on the surface have recorded pressure tides that move around the planet each day, driven by sunlight heating the air and by the scale height of a thin atmosphere, and these tides gently raise and lower the pressure at a given place in predictable fashion, a planetary heartbeat superposed on the larger seasonal breathing between poles. The quiet anomalies that invite thought are modest in scale but rich in possibility. Methane plumes measured from orbit and at the surface do not always agree, suggesting that local release and rapid removal may occur in patterns that depend on wind and on chemistry at the ground. The presence of briny streaks, once thought to be recurring slope lineae, now appears to be more strongly tied to dry flows of grains, yet the salt chemistry present at many sites shows that water, though scarce, has left a signature that endures in minerals that formed with it. The rate at which dunes migrate, measured by comparing images over years, is slow enough to comfort, but real enough to show that even under a thin sky sand can move rivers of its own. The European Space Agency's ExoMars Trace Gas Orbiter circles Mars and watches for faint gases, while mapping the distribution of water in the near surface. The National Aeronautics and Space Administration's orbiters keep a long weather log, and the rovers carry sensors that read air and ground with a patience that suits the planet. Together they reveal a world that rests in quiet rhythms, frost at dawn, dust lifted by midday gusts, temperatures that swing widely between day and night ice, that shifts over ages as tilt changes, and a sky that breathes with the polar caps. The most relaxing truth about Mars is that it keeps a memory of water without needing to rush it into the present. The planet holds its ice under dust, and in poles lets carbon dioxide frost draw patterns, and fans in spring, moves dunes by small measures each year, and shows through thin air a set of gentle processes that persist from season to season. The questions that remain add to the calm rather than disturb it. How quickly do the polar layers grow? How often does methane rise? How deep are the buried glaciers? How does water vapor drift from morning frost into the midday sky? Each will be answered by continued watching rather than by sudden insight, and in that watching, Mars offers a quiet stage where breath and frost set the tempo under a sun that is steady enough to repeat the show. Earth and Moon move together in a slow duet that sets a global heartbeat, and the rhythm of that dance is felt in the rise and fall of seas, in the stretch and release of rock, and even in the faint breathing of the air. The Moon keeps one face toward Earth as it circles in a period of a little more than 4 weeks, a synchronous turn learned through long tides that once were stronger and are now calm, and Earth spins beneath that gaze, turning oceans and continents through bulges of water drawn by gravity. The bulges do not align perfectly with the line between Earth and Moon because the oceans need time to move, and friction with the seafloor, and with coastlines drags the swell a little forward. That slight lead is enough to tug the moon ahead in its orbit, adding energy to its path while Earth pays with a minute slowing of its spin. The result is a gentle recession, a drift of the moon outward by a few centimeters each year. Measured with quiet precision by laser pulses sent from Earth to mirrored panels left on the lunar surface by Apollo astronauts and by lunar-cod rovers, and timed on return to the nanosecond, a practice called lunar laser ranging that has continued for decades. As the moon recedes, the length of Earth's day increases by a few milliseconds per century, a change so small that only careful clocks can hear it. Yet over millions of years it accumulates, and ancient corals and tidal rhythmites keep a fossil record of days, once shorter, and months once fuller. The tides themselves are not only of water. Rock also bends, rising and falling by subtle amounts as the moon passes overhead, and the atmosphere swells and eases with pressure tides that step around the planet each day, adding a soft modulation to winds. In the oceans, the global wave splits around islands and basin shapes, setting up amphidromic points, where the tidal range is near zero, and rings around them where the range grows, so that some coasts see only a small lift, and others see meters of rise and fall, all following the same skyborne metronome. There is no single tide, but many layered like harmonics in music. The principal lunar tide that follows the moon, the solar tide that adds and subtracts in phase to make spring and neap tides and longer cycles set by the tilt and wobble of the lunar orbit. Over a period of about 19 years, the plane of the moon's path precesses, changing how far north and south the moon appears to travel, and shifting tidal ranges by modest amounts that coastal communities have quietly built into long almanacs. Eclipses ride these alignments. When the moon passes between Earth and Sun near a node of its orbit, the shadow touches the surface, and day becomes twilight along a narrow path. When Earth slips between Sun and Moon, the lunar face glows copper as sunlight filters through the air and bends into the umbra. These events arrive in families tracked by an old cycle lasting a little more than 18 years, a cadence that does not rush and that comforts by its return. As the moon continues to drift outward, its apparent size in the sky shrinks slowly, and in a far future the geometry will no longer allow total solar eclipses, only gentle annular rings of fire. The change will be so gradual that many thousands of generations will pass before the last totality fades. The barycenter of the Earth-Moon system lies beneath Earth's surface, yet not at its center, a point in the mantle around which both bodies orbit, and this shared motion adds a slight sway to Earth as it circles the Sun, a sway that imprints on tides and on the timing of seasons with a finesse that is easy to miss and pleasant to realize. The energy shuffled by tides does quiet work. In narrow straits and over shallow banks, rushing water stirs nutrients and mixes warm and cold layers, lifting tiny life and setting conditions that anchor food webs, while in the deep ocean, internal tides formed where surface tides run across underwater ridges carry energy into the interior and break into turbulence that helps the ocean overturn on vast, slow loops. On land bays shaped like funnels can enter gentle resonances that amplify the tide to dramatic but orderly ranges, while other coasts tucked behind sills or opening to broader shelves keep the daily rise small. A geography lesson written by Gravity and Contours. The moon's surface itself bears the record of tidal history in a quieter way. Within its interior long ago the repeated flexing would have warmed rock and influenced how the early crust set, and even today the moon, though tidally locked, feels tiny shifts as it travels its slightly elliptical path, rocking by a little seen as libration that lets careful watchers glimpse around its edges over the course of a month, a friendly reveal that repeats forever. On Earth, the crust heaves by centimetres as tides pass enough to matter for precise instruments, and for the patient networks that watch, continents drift and strain, accumulate along faults, and timing. Those motions help scientists subtract the tidal signal and read the slower tectonic message beneath. The calm anomalies within this system are invitations rather than contradictions. The rate of lunar recession is not perfectly constant, because ocean basins change with plate motion and with sea level over millions of years, altering how efficiently tides drain energy from Earth's spin. Records from corals and sediments show epochs when tides were likely stronger or weaker, and models that include ancient geography explain how a different arrangement of continents could have tuned the planet into or out of a resonant state, much as a bowl finds a pitch when tapped. In the present epoch, the Atlantic basin's shape supports stronger semi-diurnal tides than many other basins, a condition that will evolve as lands drift on their long journeys, and that will in deep time adjust the rate at which days lengthen and the moon recedes. The moon's orbit is also inclined by several degrees to Earth's equator and to the plane of Earth's path around the sun, and the interplay of these tilts combined with the elliptical shape of the orbit produces small variations in the timing and height of tides from fortnight to fortnight, and from season to season, a gentle complexity that long tables capture with accuracy, good enough for harbours and fishers, and for instruments that must know the exact height of the sea to millimetres. The quiet measurement of the Earth-Moon distance by laser begun in the late 1960s continues through nights of clear air in observatories that send short pulses up and catch a handful of photons on return, and over time the pattern reveals not only recession, but also minute wobbles that test the bedrock of gravitation with an elegance that fits the system's calm. Earth's rotation followed by networks of radio telescopes, timing distant quasars, and by the swing of gyroscopes and the drift of satellites, shows the tiny lengthening anticipated by tidal theory, with additional short-term jiggles driven by winds currents and exchanges of angular momentum within the fluid parts of the planet. There is comfort in how these huge and small motions align across instruments and methods. The moon drifts outward at a rate that matches the energy lost by Earth's spin and the heat dissipated by tides. The day lengthens by an amount that records that trade. The fossil and rock record agrees in its broad strokes. Life on Earth has long tuned itself to these cycles. Tidal flats inhale and exhale water on schedules that set feeding times. Many coastal species release eggs and larvae to the spring tide's stronger reach. Human calendars carry the pull of months named for the moon. The pulse of a spring tide under a full moon or new moon remains a shared experience on shores around the world. The most relaxing truth is that nothing here hurries. The moon recedes by the width of a fingernail each year. Earth's day adds the span of a blink over a lifetime. Tides advance and retreat with the certainty of breathing. The soft questions that rise carry no urgency. How will future arrangements of continents reshape the tide? How will changes in sea level adjust the efficiency of energy loss? How long until the distant balance brings Earth into a state where one hemisphere forever faces the moon, and both spins have slowed into a mutual calm that tides eventually seek? That final state lies beyond the lifespan of the sun, and so the duet will play on without reaching its last chord, an unended peace that soothes by its constancy. Under that ongoing music the world turns, the sea leans and levels, and the moon keeps watch, a companion whose distance grows by tiny steps that instruments can see and that minds can hold as a gentle measure of time. Venus turns so slowly that a single day there lasts longer than its year. A stately retrograde spin of about 243 Earth days, set against an orbital period of about 225 Earth days, and this unhurried rotation allows the planet's high clouds to take the lead racing around the world in only about 4 Earth days in a steady super-rotation that slides like a bright veil over a hidden landscape. The air is thick and warm throughout, made mostly of carbon dioxide with a small share of nitrogen, and threaded by clouds of sulfuric acid droplets that gather between altitudes of about 45 to about 70 kilometers, where temperatures and pressures fall into a range that would feel more familiar to human instruments than the extreme conditions at the ground. Below the clouds, heat builds and rests, and at the surface the pressure stands at roughly 90 times that of sea level on Earth, with temperatures that hover near 700 degrees in the scale that begins at absolute zero heat, gentle only in the sense that it does not change quickly, lingering across plains and mountains beneath a sky lit not by direct sunlight but by a bright golden haze. Radar sent from orbit and from Earth has opened that haze with patient pulses. In the early 1990s, the spacecraft Magellan from the National Aeronautics and Space Administration mapped the surface almost completely, painting in microwaves a planet of broad volcanic plains, long sinuous channels carved by very fluid lavas, tall shield volcanoes, steep-sided domes and plateaus of intensely deformed rock called tesserae that rise like crumpled islands from a darker sea. The tesserae record compression and extension, written in crisscrossed ridges and valleys, a geology that seems both old and restless, while the plains smooth over large areas carry craters so few and so evenly scattered that many scientists infer a long history of resurfacing by lava that kept erasing parts of the record at a slow, persistent pace. The rotation and the thickness of the air combine to make weather that is at once energetic and calming, with large-scale waves that travel around the planet and produce the famous Y-shaped feature seen in ultraviolet images, and with each pole crowned by a vortex that organizes the clouds into spirals that change shape without losing their place. The European Space Agency's mission Venus Express watched these patterns for years, beginning in the year 2006, tracing how the upper winds shift with local time, and how planetary scale waves modulate the super-rotation, while the Japanese Aerospace Exploration Agency's spacecraft Akatsuki, which arrived in the year 2015, carried cameras tuned to multiple wavelengths and recorded a vast stationary bow-shaped wave arching across the cloud tops above a highland named Aphrodite Terra, a gravity wave likely raised by lower air flowing over topography and reaching to high altitude where it stayed fixed relative to the ground while air streamed through it. This stationary wave suggested that even in the dense atmosphere, the slow pulse of surface features can play a role in the grand circulation, a gentle coupling between stone and sky that persists across months and perhaps years. The composition of the clouds is simple, yet subtle. Sulfur dioxide rises from below and meets water vapor at mid-altitudes, forming droplets of sulfuric acid that scatter sunlight and give the planet its brilliant brightness in Earth's sky. And at the very top of the clouds, ultraviolet absorbing particles tint the view in ways that instruments can read but not fully explain, a mild mystery that keeps observers watching for changes that drift with the long day. Beneath the clouds, the lower atmosphere wraps the planet with nearly uniform temperatures from equator to pole, an isothermal calm supported by the slow rotation and by the way dense air carries heat efficiently around the globe. Winds there are far slower than at the cloud tops, but still steady, and combined with the immense pressure they smooth the daily cycle into a long even glow. On the ground, radar images reveal lava plains stitched by wrinkle ridges, pancake domes that may have formed from thick silica. Rich lavas extruded at gentle rates, and coronas broad oval structures bounded by concentric and radial fractures that many models tie to plumes of warm mantle, material lifting and spreading under the crust. These features distributed widely and overlapping in places speak of a planet that has released heat not through drifting plates, as Earth does, but through convection that swells and relaxes the outer shell in place, a hauntingly quiet form of tectonics that reshapes the surface over spans as long as millions of years without a single global mode of motion. The polar vortices are among the most soothing puzzles. Each is not a single eye, but a shifting arrangement of two warm cores that dance around each other in slow steps, embedded in a broader spiral that draws cloud arms inward, and the entire structure migrates and morphs, while holding to its polar home like a candle flame that flickers yet never leaves its wick. Measurements of trace gases in the upper air show cycles tied to day and night on the long Venusian day, including temperature tides that climb and fall, and that are thought to help drive the superrotation by transferring momentum from waves into the mean flow, a quiet mechanical exchange repeated again and again like oars dipping into a still lake. The surface chemistry holds its own restrained intrigue. Radar echoes from some highlands on the night side appear unusually bright. A signature first read as possible, metallic frost made of lead, or bismuth sulfides condensing in cold upper slopes, then reconsidered as perhaps roughness or rock texture, and the truth may mix both ideas in different regions, an elegant uncertainty that invites more careful looks. Reanalyses of the Magellan data published long after the mission suggest that in at least one place near a volcano named Mat Mons, a vent changed shape over the course of 1 year, consistent with a small eruption, or with the gentle collapse of a conduit, a hint that volcanism on Venus may not be entirely in the past, but may continue at a tempo too slow or too veiled to announce itself strongly. The air also carries the signature of gases that vary with height and time. Sulfur dioxide levels in the upper clouds rise and fall on scales of years, perhaps as deeper plumes deliver fresh gas that later settles and reacts, and thermal emission from the night side shows variability that maps onto cloud opacity and to waves that snug around the equator like a soft belt. The planet radiates back to space a heat field that is nearly uniform in longitude at the level of the cloud tops, another sign that the slow rotation and deep air layer together smooth the day and night into a single extended afternoon. Lightning has been hinted at by bursts of radio noise and by flashes recorded by orbiters and landers, though the details remain gentle questions, and if present such discharges would take place within the cloud decks where convective cells rise and fall at measured rates. At the ground, the rocks are altered slowly by the hot dense carbon dioxide, and by trace gases in a process that laboratories on Earth simulate in pressure vessels, and the results suggest that some minerals transform to more stable forms over timescales of years to centuries, meaning that even without running water the surface is not chemically still. Over deep time, Venus may have known oceans if its early atmosphere was thinner and if sunlight weaker, a possibility that climate models explore by treating clouds as reflective blankets that could have kept temperatures moderate, and if such seas did exist, they would have left their memory in ratios of hydrogen isotopes measured today, which show an enrichment consistent with the long loss of lighter hydrogen to space. Yet this story carries no urgency, now only a soft background to a present that is stable in its warmth and dense in its air. Future missions that are now planned will approach this calm world with new ears and eyes. The European Space Agency will send Envision to sound the crust and read the surface chemistry with radar and spectrometers, while the National Aeronautics and Space Administration prepares 2 missions named Da Vinci and Veritas 1 to sample the atmosphere directly during a deep descent, and to map noble gases and their stories of origin, and 1 to remake the radar portrait with finer focus so that small changes and subtle structures can be seen. The Japanese Aerospace Exploration Agency's Akatsuki will continue to watch the clouds, and together these efforts will test whether the superrotation holds the same pace across years, whether stationary waves recur over the same mountains, whether vents open and close without haste. The most relaxing truth about Venus is that even at such high temperature and pressure, the system behaves with steadiness. Clouds glide around the planet in a repeated pattern. Polar spirals keep their posts, bow waves hold to their highland anchors, and the surface, though active across geological time, presents a scene that changes only slowly as lava's cool tesserae rise and erode, and plains accept new veneers. The quiet questions that follow are gentle and open-ended. How does the atmosphere keep its swift run over a body that turns so slowly? How deeply do the waves reach? How often do small eruptions repaint a patch of ground? How much memory of early water survives in rocks now bathed in warm haze? Each is an invitation to watch without hurry, to let Venus teach in its measured way, that even extremes can be orderly, and that a planet with a very slow turn can host winds that sing softly and continuously above a landscape that endures. Mercury circles close to the Sun in a path that brings it through intense light and deep shadow, and its own slow spin keeps time in an unusual way. It turns exactly 3 times for every 2 trips around the Sun, a steady resonance that makes a single solar day on Mercury last 2 of its years. The result is a landscape that bakes for months under a high sun, and then rests for months under a dark sky, with temperatures on the day side rising high enough to glow in infrared, while the night side cools toward the deep cold of space. Yet near the poles, a different calm holds. Because the planet's tilt is only a fraction of a degree sunlight, there skims the horizon, and crater floors can remain in permanent darkness for millions of years. Radar from Earth once picked out bright patches in those polar shadows, and later a patient orbiter from the National Aeronautics and Space Administration confirmed the presence of water ice mixed with dark insulating material, a quiet store of frost kept safe a short planetary step from the Sun. The ground itself carries the record of stress and time. Across smooth plains of ancient lava, long cliffs called lobat scarps run for hundreds of kilometers, their faces breaking the surface in tidy steps. These are contraction wrinkles made as the interior cooled and the whole planet shrank a little, leaving gentle folds that tell of a world settling into itself. Elsewhere, clusters of small bright depressions called hollows dot crater floors and central peaks, as if some volatile ingredient near the surface had been lifted away into space, leaving crisp rims and pale interiors that resist darkening, and that speak of ongoing surface change that is subtle rather than violent. The crust is poor in iron compared with familiar basalts on Earth. The plains are rich in magnesium and sulfur, and the core beneath is very large for a body this size, a metal heart that likely remains partly liquid. Precise tracking of an orbiter's motion and the small rocking of the planet as it rotates show that a fluid layer still decouples the solid mantle from the core, and that fluid supports a weak but real magnetic field, only a small fraction of Earth's in strength, and shifted a little toward the north. That offset field shapes a magnetosphere so compact that it brushes the thin charged wind from the Sun only a short distance above the ground, and the boundary flexes in response to solar gusts in a rhythm far faster than at Earth. The sky above Mercury is not an atmosphere in the ordinary sense, but an exosphere, a near vacuum sprinkled with atoms released from the surface by sunlight, by the slow rain of micrometeoroids and by gentle sputtering from energetic particles. Sodium and potassium glow in dawn and dusk, calcium and magnesium appear in faint traces, and a long delicate tail of sodium streams away from the planet on the night side, visible to sensitive instruments as it stretches along the orbit like a pale thread. Each sunrise refreshes this envelope as light lifts atoms from warm ground, and the solar wind rearranges the cloud, and each long night allows some species to settle back. On the surface, regolith grains charge and discharge in the sun's light and static forces, may loft the finest dust a small distance in slow hops at the terminator, the line that divides day from night, a quiet dance of particles over gentle slopes. Impact craters, some with bright ray systems, record a history of bombardment that was heavy in the distant past and light today, though still a little more frequent than at Earth, because Mercury lives deeper in the stream of dust and stone that crosses the inner system. Between older craters lie volcanic plains, whose smoothness and flow margins show that long ago lava welled up through fissures, and flooded basins then cooled into the broad level surfaces that make the planet's face so even in many regions. Against this small world's steady order stands the sun's larger rhythm. The sun's activity waxes and wanes in a cycle of about 11 years, bringing periods of more sunspots, more bright points called faculae, and more openings in the outer atmosphere called coronal holes, which let fast streams of charged particles sweep outward. When such streams reach Mercury, the compact magnetosphere breathes in and out, reconnection flashes through magnetic lines, and charged particles touch the surface in small moving ovals, sputtering atoms that add to the exosphere. Yet even at such times the scene is not chaotic. The cycle repeats, the patterns hold, and the surface takes this weathering in measured doses that leave fine changes spread over eons. The sun's photosphere, seen from Mercury's day side, boils in granules the size of small countries, bright upwellings of hot gas that fade at their edges, while high above loops of magnetic field guide glowing plasma into arches that stand and lean in slow motion. These features rise and settle without haste compared with a Mercury day. Missions dedicated to the Sun from the National Aeronautics and Space Administration and from the European Space Agency fly close and far to watch switchbacks in the solar wind, to trace the origin of slow and fast streams, and to map the way energy moves outward from the surface, and the knowledge they bring adds context to Mercury's calm response. The geometry of Mercury's rotation makes local time an elegant puzzle, because the spin and orbit resonate a region that faces the Sun at one closest approach, will face it again 3 orbits later, and the subsolar point traces a repeating pattern on the ground that ties hot seasons and cool seasons to longitude as much as to latitude. In a few favoured places near perihelion, the Sun's daily path lingers near the horizon, before rising again, making double dawns and double dusks that are more curious than dramatic. Near the poles, small topographic highs catch almost constant light, and make rare warm islets amid the cold shadows, while a few crater floors remain so dark that ice can survive for geologic time. The contrast fits readily into a mind looking for rest, a balance of near and far, warm and cold held within one small sphere. The slow contraction recorded by scarps continues in tiny increments, and now and then a fresh scarp offsets small craters by a few meters a mark, that the interior still cools and that the outer shell still adjusts. The magnetic field we can offset acts as a tracer of the core's evolution, and measurements over many years show small changes that can be used to infer motions deep below. The exosphere, though quiet, varies with seasons of the orbit and with the solar cycle, and the sodium tail brightens and fades in a cadence linked to these drivers. The calm anomalies that invite thought are gentle. How ice endures under a sun so near. How hollows form and enlarge without heat or liquid water. How a small dynamo sustains a field within a core that dominates the planet's mass. How the sodium tail responds to meteor streams in brief soft glows. Answers come through missions that pass and orbit through radar beams sent from Earth and through long watches that compare one Mercury year to the next. An international spacecraft now on its way with the European Space Agency and the Japan Aerospace Exploration Agency will circle Mercury in the coming period with 2 orbiters that together will map fields, particles, and the surface in greater detail, listening for the exosphere's pulse, reading the scarp networks for patterns of stress, and tracing the magnetic lines as they open and close to the wind. None of this seeks to hurry the planet. It only keeps company with a world that moves close to a star yet keeps quiet reserves of cold, that carries a metal heart and a soft halo of atoms that writes its history in fine lines rather than in sudden breaks. The most relaxing truth about Mercury is that nearness to the Sun does not erase delicacy. Permanent shadows hold ancient frost while nearby peaks glow in near-constant light. A long day makes heat rise and fade in a slow arc instead of a quick blaze. A small magnet casts a small shelter that still suffices to order space above the ground. Around all of this, the Sun keeps its broad cycle breathing in light and particles that the inner worlds feel as seasons of space, and within that breath Mercury continues to turn a close companion that wears both fire and ice with ease.